Hi guys, it's Mrs. Millison. Okay, our next lesson is determining if two variables are independent of each other. Okay, in statistics, a lot of times you're working with two types of variables and you want to know if there's a relationship between the two. Okay, if there is a relationship, then they are dependent on each other. Not in the sense that one causes the other. Just because two variables have a relationship or an association does not mean there's a cause and effect. So association does not equal causation. It might be something outside of both those variables that's causing the change, okay? Now, if two variables are independent, it means there's no relationship, okay? And there's no association between the two. So then we will just move on to another, to research another type of relationship. But if we can have evidence that two variables are dependent, then we can do some further research to see more about the dependency, more about the relationship. Okay. All right, I have unofficially asked 158 people their favorite candy, okay? And then, just from these few types of candy, and then I categorize them by eye color. So I want to know, is there a relationship, or are eye color and candy, favorite candy, independent, okay? Or is there a relationship? Now I wanted to cover up the totals. Anytime you're given a two-way table, if you don't have totals, do your totals, okay? Do your column totals, do your row totals, verify your total. So there's my 185 people that I surveyed, okay? So clearly, a majority of the people had brown eyes. 40 people had blue, 25 had hazel, 10 had green, and 10 had another color, okay? Of the 185, 94 like Reese's Peanut Butter Cups, obviously the most preferred candy. 18 people like Snickers, 37 liked M&Ms, and so forth. So putting these totals over the table total, those are your marginal distributions. And that'll come in handy later on when we do probability, okay? But in order to determine if eye color and favorite candy are independent, we need to do conditional distributions, okay? So I'm going to do it by eye color. So I'm going to do it by, let's see, brown, blue, hazel, green, and other. Okay. Oh, sorry, you can't see that. Let me fold my paper here. So, oops. Fold my paper so we can move that up a little bit. I'm going to do a little bit by hand now. It's all typed out. Okay. So I'm going to look at all the conditional distributions for all the people that have brown eyes. Okay. So this is going to be for Reese's Peanut Butter Cups. This is going to be for Snickers. And we got M&Ms, Skittles, and other candy. Okay, so I'm just going to draw my lines for my conditional proportions. Now, since these are for all the people with brown eyes, all of these denominators have to be the total of my brown-eyed people, which is 100. Okay, oops, move this up. So, brown-eyed people that like Reese's Peanut Butter Cup, that's 53 over 100, which is obviously 0.53. Snickers was 9, which is 0.09. M&M's is 19. Skittles is 8. And other is 11. That's a terrible looking 8. Okay, now all of these should add up to be 100%, and indeed they do, because that is 100% of the brown-eyed people. Okay, let's do blue simply because I don't want you to think that that's a percent. That 100 is a total number of people. Okay, so let's do blue. Now, of all the blue-eyed people, these will all be over 40 because that is the total of blue-eyed people in my survey. So Reese's Peanut Butter Cup is 19, Snickers is 5, M&M's is 10, what is it, Skittles is 4, and other is 2. And of course I do my proportions. This is 0.475, I'm sorry, my decimals, 0.125, 0.25, 0.1, and 0.05. And again, all of these will add up to be 100% or 1.0, right, if I'm doing the decimals, because these are the breakdown of all the blue-eyed people and the different candy they like, okay? So I have to do my total for hazel, for green, and other, okay? I went ahead and already typed it up, so we'll look at it. Okay, so here's my conditional distributions. There's the brown that I just wrote and the hazel I just wrote. The blue. So my hazel are all out of 25, okay? And again, these all add up to be 100% or 1.0. Greens are all out of 10, and then other is also out of 10, okay? These totals this way aren't going to be anything consistent, okay? These totals going horizontally aren't going to make any sense. So you want to do your totals per the category that you are grouping them by. We're grouping them by eye color. Okay, so from our conditional distributions, we're going to create a segmented bar graph. So I'm going to have a bar for brown, a bar for blue, a bar for hazel, and so forth. And each bar is going to be 100%. So I have to take the 100% brown bar and break it up into 53% Reese's Peanut Butter Cups, 9% Snickers, and so forth. Okay, so I've already done that, made it look all nice and pretty. Okay, so here's my brown bar. Let me make sure you can see everything. Here's my brown-eyed bar. So this part is Reese's Peanut Butter Cup, so this is 53%. This part is Snickers, okay, and that's about 9%. M&M's is about 19%. Skittles, about 8%, and others 11%. So this bar represents these percentages, okay, and I have the different textures or patterns for the different candies. Okay, so here's my blue bar, represents all my blue-eyed people. So about 48% like Snickers. Yeah, it's about 48%. About 13%, so that should be about 12 or 13. Let's go from the top. 5% like other. Yeah, it's about 5. And that's 10 that like Skittles. And here's 25% that like M&M's. Okay? So my segmented bar graph is a way to visually represent your conditional distributions. And I think this is a lot easier to read than looking at a sea of numbers. Okay? So what we can do is we can look at our segmented bar graph and say, is there a relationship between candy preference and eye color? Are they independent or dependent? Well, the thing I always remember to say is if the bars are broken up differently, then the variables are dependent. So different equals dependent. And that's easy to remember because the two D's, okay? So do these bars all look broken up differently? I think so. I mean, if you just follow this, it's small, it's wide, it's small, it's down, it's up. You know, these are clearly all large, but they're not the same height, okay? So I would say, because the distribution of candy preferences are different for each eye color, we have evidence that candy preference and eye color are dependent, not independent, okay? So if they're dependent because the distributions are different, it means there is a relationship, there is an association between eye color and candy preference, okay? So after you make that statement, then we just have to talk a little bit about the data. Well, I'm going to say something about Reese's Peanut Butter Cup. Reese's Peanut Butter Cups are clearly the most popular for each eye color, okay, without a doubt. Blue-eyed people prefer M&M's more than hazel-eyed people, definitely, okay? People with green eyes prefer other types of candy compared to people with all the other different eye colors, okay? And then I wrote Snickers. Where's Snickers? Snickers are the least preferred among hazel, okay? So that looks pretty close, and I can see that that is pretty close, but that is the least preferred. That is the smallest proportion of people with a specific eye color that like Snickers, okay? So you can say anything you want about the data, just make a couple statements, okay? So here is my little description that I just read to you, okay? Okay, now, in addition to a segmented bar graph, I wanted to show you a mosaic, okay? Now, a mosaic is going to be a segmented bar graph, but the widths of the bars are going to be related or numerically associated with the number of people in the survey, or the number of observations per category, per variable that you're grouping on, okay? So clearly, this brown bar, out of 100 people, this brown bar should be the widest, okay? These two are only 10 from 100. So green and other, these bars should only be 1/10 the size of brown, and so forth. You with me? The blue-eyed people, 40, should be a little less than half of the width of the brown, and then hazel will be obviously a quarter of the brown. Okay, so I went ahead and created a mosaic so you can see what that looks like. So you'll see the actual breakdowns of the categories are the same, okay, for each eye color. Oh, can't see that. For each eye color, okay, so here's other and here's other. But the widths are different. So clearly there was more, I can see from this graph that there were more people with brown eyes in this survey, okay. This looks a little less than half of that, so, you know, a lot of blue-eyed people, but not as many brown. And then the green, the other, I know didn't have that many people, okay? So the mosaic just allows us to see the relationship between the number of observations in each category that you're grouping by, okay? But the widths of the segments should all be the same, okay? So these kind of go hand in hand with each other. This just tells you a little bit more, okay? All right. Now, my next question I wanted to ask is, now you've seen what a segmented bar graph looks like when the distributions are different, okay, and there is an association. What if there was no association? What if it didn't matter what eye color you had? Everybody, every eye color group had the same percentage of people that liked Reese's Peanut Butter Cups, okay? Well, in that case, just to show you what it looks like, if eye color and candy were independent, okay, it means there would be no relationship, no association. The bars would all be exactly the same. So the same percentage of people like Reese's Peanut Butter Cups, the same percentage of people like Snickers, the same percentage of people like M&Ms, no matter what eye color, okay? So if I had created this bar graph, this segmented bar graph, I would say that eye color and candy preference are totally independent. It doesn't matter what color somebody's eyes are. Majority of people are going to like Reese's Peanut Butter Cups. Doesn't matter what their eye color is, okay? Smallest group of people are going to like Skittles. Doesn't matter what their eye color is, okay? So when two variables are independent, the segmented bar graph should be the same, okay? All right, my last example is going to be, I Googled some stuff on the internet, and I wanted to know car color preferences, okay? So I looked at 3 regions of the world, Europe, Asia, and North America. And I got this off of some website. What is it, Axalta Coating Systems? I guess they paint cars or they track car color. Who knows? Okay. Now, these distributions are already in percents, okay? So if I added all these up, it would be 100%, added all these up, it would be 100%, and so forth, okay? So obviously I have to group by country. So when I do my segmented bar graph, I'm gonna have a bar for Europe, a bar for Asia, and a bar for North America. Then I'm gonna break them up, okay? So I wanna know, is there a relationship between the region somebody lives in and their car color preference, or are the two variables independent, okay? And again, I said I don't need to create conditional distributions because these are already in percentages or decimals, okay? So I went ahead and created a pretty segmented bar graph on Excel, and I matched the colors of the cars, okay? So clearly, let's look at Asia. 48% of the cars are white, and then all the other ones are pretty small compared to that. So black is the next popular at 17%, silver at 11%, so we can see that. So here's my 48% of white cars in Asia, 17% of black, 11% of silver, and so forth. Okay. All right. From this segmented bar graph, real quick, I can't do a mosaic here because I don't have counts. Okay. These are already percentages and decimals, so I really don't know how many cars they counted in Europe or Asia or North America, so I can't do a mosaic. So I have to just do the segmented bar graph. All right. What do you guys think? Is there a relationship between car color preference and region? I would say yes. These distributions are clearly different. Okay, if there was no relationship, all of the white block boxes would be the same size and same location. All the black boxes, the silver, the beige, the gray, and blue, and they are clearly not. I mean, this guy's got yellow, and I can barely, oh, there's a little bit of yellow. I can barely see yellow there, okay? So since the distributions of car colors are different for the 3 regions, we have evidence that car color and region are not independent. They're dependent. There is a relationship or an association, Okay, so depending on where you live, it's probably going to impact the color car you have. Who knows? Okay, but there is a relationship between region and car color. Okay, white appears. Okay, after I've made that statement, let's say something about our data. White appears to be the most favored car color for all the regions. People in Asia seem to prefer gray cars. Where's gray? Less than the people in Europe and North America. People in North America seem to prefer red cars, here we go, more than people in Europe and Asia. And then all three areas seem to have the same preference for silver cars. Where's my silver? There's my silver. These all seem to be about the same. And you can see that. These are all about the same. Oh, you can't see. These are all about the same numbers. Okay? So, again, when you're asked if two variables are independent or dependent, if the distributions are different, they are dependent, which means there is an association. So you make that statement. Okay? Then you just simply say something about the data. You can talk about the most popular, the least popular, somebody that likes something less than the other two, things that are similar. Okay, just make a couple statements about the data. Okay, all right, so that is why we have learned about two-way tables and conditional distributions in this lesson. The marginal distributions and conditional distributions will come back when we get to probability in later chapters. Okay, thanks a lot and see you next time.